Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, today's topic hybridization and aromaticity. These two topics are the most important topics with respect to your concepts. So you have to be attentive. So coming towards first topic hybridization. Hybrid means when we combine two things. Here, this hybridization is concerned with chemistry in which orbitals are hybridized in such a way that we can just tell that this orbital has such type of percentage or ratio. Because when I give you lemon juice, you can identify it due to its flavor that this is lemon juice. When I give you mango juice, when you taste it, without seeing, I just tie a cloth on your eyes, or I tell you to close your eyes and then taste any juice which I give you, like mango juice. You can identify orange juice or uh, pineapple juice. You can instantly tell due to its flavor that this is this juice. But when I combine all the juices, I mix all the juices, now you are not able to tell that what type of juices are present. Due to its fragrance, odor, or taste, you can tell maybe this, you are not sure. Or if you tell that this type of juice is present, this type of juice is present. So same here, that orbitals are mixed or combined in such a way that no S or P character is present, and you can calculate its percentage, that how many percentage of S is present, either 25% and P 50%, 33%, 66%, or 75%. So same hybridization, orbital hybridization is nothing but a mathematical approach that how orbitals are mixed, that is mixing of individual wave functions for S and P orbitals to obtain wave functions for new orbitals. And this way you can give different proportions, that like in sp3 S has 25% and in sp2 S has 33% contribution, and in sp it is with 50% contribution. So the electronic configuration of carbon is 1s2, 2s2, 2p2. But 2p2 means that carbon should be divalent, but it is not actually divalent, it is tetravalent. How tetravalency will be verified? Because one electron in the 2s orbital is excited and promoted to higher energy level in P. And as a result, one electron in 2s and uh, three separate electrons in separate px, py, and pz respectively. So you get four orbitals with single electrons, and to make a bond, two electrons are required. So one electron in each orbital and one electrons from coming element or atom. If we take the example of CH4, what happens? C, carbon has sp3 unpaired electrons, hydrogens. If they attach directly with 1s of carbon, one hydrogen from hydrogen bond is formed, and 3p electrons, 3 hydrogens combine to form. In this way also 4s, there was possibility of 4sp3 because 1s and 3p's, 4 orbitals are involved in bond pairing. But as you know that s and p are actually energy levels. Orbitals mean energy levels. They differ in their energy levels. S is lower energy level, whereas 3p orbitals have higher energy level. So this bonding is not known as 4sp3 hybridization. Actually, what happens that before forming bond with hydrogen, and you have to be careful that hybridization doesn't mean hybridization of electrons. No, hybridization of orbital. So s energy level and 3p orbitals, they are mixed in such a way that all these 4 orbitals, one from s and 3 from p, they are combined to form hybridization, in where all 4 they are of same energy level. S is not in lower energy state and 3p's are not at higher level. They all 4 sp3 of same energy level. After, because this, why hybridization is taking place, that S is of lower energy level and 3p's are of higher energy level, but when they combine, these 3p's and s, total 4 energy levels, are of same energy level, which is lower than 3p orbitals energy level. So these orbitals feel comfortable with lower energy level because anything, any atom, element, orbital which is lower in energy state becomes stable in that environment. So before the distribution of electrons to make bond pairs, orbitals, they mix carbons for 1s and 3p's orbitals, they mix in such a way that the energy level of p orbital is lower than actual p, which is not hybridized, and s is slightly higher than unhybrid orbitals when it was in unhybrid s orbital. Now after hybridization, one electron is present in these 4 orbitals. 4 hydrogens, they are paired up with these 4 hybridized orbitals and bond pair is formed. This is simple for sp3 hybridization, where all orbitals are hybridized. In sp2 hybridization, as you are seeing that 1s and 2p's orbitals are involved. So these 3 orbitals are mixed. One is not taking part in the mixing of orbitals. So 1s and 2 orbitals, they are combined, they are mixed in such a way that it is neither energy level of s before hybridization and neither it is, these are 2p orbitals energy level before hybridization. After hybridization, the energy level of those p orbitals is less as compared to energy level of unhybrid p orbitals. Now in sp, what happens, only 1s and 1p, 50-50% of each, 1:1 ratio, s and p orbitals, they are hybridized. and other two orbitals are, they are not taking place in hybridization. So after hybridization, one electron from another carbon and one electron from oxygen is taking place for bond formation. So in 4sp3, 4 orbitals are involved with percentage 25 s character and 75 p character, 1 is to 3 ratio. In sp2 hybridization, 1s and 2p orbitals are hybridized, meaning 1 is to 2 ratio, 1 ratio s and 2 ratio p, or if we calculate its percentage, it is 66% p character and 33% s character. And in case of alkenes, s character and p character both are 50% each, 1 is to 1 ratio, they have 1 is to 1 ratio. Now as the system after hybridization attained less energy, so it is stable in the environment, and after hybridization distribution of electrons is taking place. Clear? Now the geometry, when sp3 bond is formed, it is always tetrahedral geometry, it is always tetrahedral geometry, when like methane. And again sp2 in carbon chemistry, example of alkene, sp2 hybridized, it is trigonal, it is planar, whereas sp3 hybridized tetrahedral geometry is, you cannot draw it on the paper or you cannot draw on the whiteboard, because you have, until and unless you are shown the model or you see the model, you will visualize actually its angles and geometry in the space. It is 3D version sp3. sp2 is 2D version, you can draw it on the paper because it has 120-degree angle, trigonal planar. In tetrahedral geometry, the bond angles are 109.5 degree. In sp, it is linear, 180 degree. The bond lengths in all the three, alkane, alkene and alkyne, are different bond lengths. C single bond C, C double bond C, C triple bond C, they have different bond lengths, they have different geometries, they have different angles, and they have no doubt different energies. So what hybridization is, it is nothing but a mathematical approach that involves the mixing of individual wave functions for s and p orbitals to obtain wave functions for new orbitals, and these new orbitals are hybrid atomic orbitals which have lower energy than before hybridization, and the electrons can then be distributed in these hybridized orbitals for bond formation, but they have to follow principles of Pauli principle, that no more than 2 electrons in each orbital, and they have to reside in that orbital with opposite spin. No electrons with same spin can be accommodated in the same orbital. These are the orbitals which are now containing electrons in the lowest energy state of the molecule. Now the best example, alkane is the best example of ethane. Ethane is best example for for sp3 hybridization, and for sp2 hybridization, benzene. If we take the structure of benzene, it will be very suitable because Benzene is, you're very much familiar that this is an aromatic compound obeying Huckel rule 4n plus 2 pi electron, plus it is planar. Planarities must to exhibit aromaticity. Otherwise, if it is not aromatic, the compound will not be aromatic. Instead, it is obeying 4n plus 2 pi rules or Huckel rule, because for aromatic compounds, delocalization of single and double bond pi electrons is required, as you see in uh, benzene, that alternative single and double bonds are present, and these are actually not residing at their places, they are moving. Single and double bond character is hybrid in benzene. That is why a cyclohexagonal structure is drawn, and inside that ring is due to the delocalization of double bonds, and that is why you don't observe standard C double bond C and C single bond C characters in benzene. But as it is sp2 hybridized, the geometry trigonal planar is observed and angle is same, 120 degree. Trigonal planar, benzene is trigonal planar with 120-degree angle. Benzene has 3 double bonds, it means 6 pi electrons. These 6 pi electrons are making a sandwich above and below the plane of benzene ring. So it is highly stable, and this is the reason that it is displaying low energy. If we calculate the energy of benzene, the theoretical energy or calculated energy is higher than actual benzene is showing its energy. So the decrease in energy, that is why due to decrease in energy, benzene is the most stable compound, and due to this reason it is not giving addition reactions like alkenes. Rather, it gives substitution reactions, not to destroy or disturb its aromaticity. If benzene gives addition reactions, it means its aromaticity will be disturbed, will be destroyed. It avoids disturbing its aromaticity. It doesn't want to destroy its aromaticity. That is why it doesn't give, benzene doesn't give addition reactions, it gives substitution reactions only. Hydrogen is replaced with any incoming group, so it means substitution reactions are preferred, not addition reactions in benzene. So why this energy, why benzene has less energy? I have given that what is the reason of less energy in benzene, because benzene is very much famous, as Kekule had done many mathematical calculations to um put up his Huckel rule theory. He worked a lot, and this rule was if any compound which is obeying Huckel rule 4 and it possesses 4n plus 2 pi electrons, but it is not planar, then don't think that that compound will be aromatic. If any compound, no doubt the basic uh, requirement to make any compound aromatic, or any compound if it is aromatic, it must obeys Huckel rule. But if it is not planar, then it will not be aromatic, because that aromaticity, these alternative single and double bond, the delocalization will be observed only if they are planar. If they are out of plane, uneven, electrons will not move. They will not be able to delocalize. So as a result, no alternative single and double bond, no delocalization, that compound will not be aromatic. Clear? So benzene, now you can, with respect to hybridization, with respect to single and double bonds, because in sp2 hybridization, double bond has some specific measurement. It has some specific bond length, but that is not observed in benzene. Carbon-carbon single bond has specific bond length, but that is not observed in benzene. So these things combined, delocalization, planarity, alternative single and double bond, they are playing part in its aromaticity, that they are obeying Huckel rule. So now it is clear that obeying 4n plus 2 is not sufficient to make a compound aromatic if it is not planar, or if any compound who that is obeying 4n pi electrons will either be aromatic if Huckel rule is obeyed, if not obeyed, or 4n pi electrons are obeyed, then that will be either anti-aromatic or non-aromatic. Details are given in your these lectures. Kindly go through properly, nicely, understand, read it 2 or 3 times to understand. Otherwise, just going through once is not sufficient to understand all the concepts. Thank you.